I wondered if a two-stage oscillator was really a free energy device. So I made my own to do a math analysis of it. First of all, let us review some basic physics. A two-stage oscillator is a gravity-powered device. Now, with a gravity-powered device, if you drop a 100-pound ball 1 foot, you get 100 foot-pounds of impact energy. Now, the trouble is that it takes 100 foot-pounds of energy to raise it back up to its starting position to be able to repeat the process. So you would have to be, that means you have to be 100% efficient in your capture of the impact energy. Now, the laws of thermodynamics state no system can be 100% efficient. So is it the case closed? If we have to have 100% of the impact energy to raise it back from the position it fell from, it seems like no free energy device is possible using gravity. However, there is a way around this, so to speak, and that's by using an oscillating system. A bouncing ball is an example of an oscillating system. The ball drops and hits the ground and then goes back up maybe 90% of the way naturally. No mechanical energy is used to raise the ball up 90% of the way. We still need 11 foot-pounds of lift energy to get it all the way back up. If it hits the ground with 100 foot-pounds of energy and we collect that energy, we subtract out the 11 foot-pounds needed to raise it back up, then we can repeat the process and we still have 89 foot-pounds of free energy. Now, what's wrong with this picture? What's wrong with this logic? Because in this case, the ball can't do both things. It can't hit the ground or a pressure plate with 100 pounds of energy and then go back up 90% of the way. The ball has to do one of two things. It has to either give up its energy on the pressure plate or it can bounce back up 90% of the way. However, there is another oscillating system, and that's a pendulum. Now, with a pendulum, we drop the ball, the 100-pound ball, 1 foot, and it rises back up 90% of the way, again, naturally. No mechanical energy is used to raise it up 90% of the way. But we still have that problem where we have to have 11 foot-pounds of energy to raise it all the way back up to a similar starting position so that it can repeat the process. Now remember, the bouncing ball fails as a free energy device, so to speak, because it cannot do both things. It cannot deliver 100 foot-pounds of energy on impact and also have energy left over to go up back 90% of the way. So the bouncing ball fails. It's different with a pendulum hooked up to a two-stage oscillator system. The reason is that the movement of the pendulum is not interfered with, yet at the same time it can cause work to be done by lifting the load weight over here. It does that by swinging forward. In this case we have two balls, each weigh 100 pounds, but this lever arm is 4 feet long, so the ball has 400 pounds of force. The same here. In this position, the 100-pound ball is 4 feet from the fulcrum, so it has 400 pounds of force. If the ball swings out 1 foot, it then has 500 pounds of force. If the ball swings inward, it has only 300 pounds of force. This difference of force on this side of the lever arm causes the load arm to rise up and down. The pendulum is not interfered with, it moves freely, and at the same time it's able to do work on this end, raising and lowering the load weight. Now for some specifications about my two-stage oscillator. The pendulum falls from a 45-degree angle on both sides. There is a stop bar that stops the pendulum at a 45-degree angle on the inside swing. The weights at the end of the load arm and at the end of the pendulum are both 8 ounces. There is a secondary weight on the load arm. This counterbalances the weight of the wooden shaft of the pendulum. Both lever arm sides are 12 inches long. The upcoming shots show how high the load weight is lifted and how far the pendulum weight swings outward during operation of the device. In a fully operational device, the pendulum weight would be mechanically caught and not be allowed to fall backwards until first advanced to the 45-degree limit. The test results varied slightly. Nearly all of them, the pendulum would stop about 1.5 inches from going all the way to the side of the triangle. 1.5 inches times 8 ounces equals 12 inch ounces. That's the energy we need to carry the pendulum all the way to the side of the triangle so that the process can be repeated, so it can swing back the other way. Another result of my test was that the load weight was raised into the air 4 inches. That means that it would then fall down 4 inches, giving us the amount of energy captured. So it's 4 inches times 8 ounces equals 38 inch ounces. This is the amount of energy generated by the fall of the weight, the amount of energy captured. So to review the results of the test, the pendulum weight needs to be lifted 1.5 inches. It weighs 8 ounces. 8 ounces times 1.5 inches equals 12 inch ounces. The load weight weighs 8 ounces. It drops 4 inches. 8 ounces times 4 inches is 32 inch ounces. Now this is roughly a 3-to-1 ratio. This is very encouraging. We only need 12 inch ounces to repeat the process, and we've captured 32 inch ounces. That is very encouraging. But it's not the end of our calculations. We have to do more. When the load weight falls, it has to lift the pendulum weight upward. This is a negative force, or a negative weight that has to be subtracted out. Now, because this is a lever arm arrangement, we multiply the 8 ounces by 12 inches, and we get 96 inch ounces for the load weight force. For the pendulum weight, we multiply 3 inches. That's where, when it swings back, it stops at 3 inches from the fulcrum. So it's 3 inches times 8 ounces. That's 24 inch ounces. We subtract 24 inch ounces from the 96 inch ounces. That's the 96 is the load force, 24 inch ounces, the pendulum, negative pendulum force, and we get 72 inch ounces. That's a net energy gain of 72 inch ounces. However, we don't use this lever arrangement calculation for the actual energy. What we want is the ratio. 24 inch ounces is 25% of 96. What we want is this percentage. Here is the same information presented in a different form. The pendulum weight is 3 inches from the fulcrum. 8 ounces times 3 inches, 24 inch ounces. The load weight is 12 inches from the fulcrum. 8 ounces times 12 inches is 96 inch ounces. 96 inch ounces for the load weight, 24 inches for the pendulum weight. Subtract that out, and we get 72 inch ounces more force on the load side. This is the net energy gain up to this point. We don't use the larger 96 inch ounce energy gain because in this instance we're capturing the energy as the weight goes straight down. That would be 32 inch ounces. We have to subtract out the other side. That's 8 inch ounces equals 25%. So we subtract out the 8 inch ounces and we get 24 inch ounces. Now this is our net energy gain to this point. Now if you use the lever system, the numbers are different, but the ratio is the same. Now we have to reduce the 24 inch ounces energy gain further because we can't capture 100% of it. I have written in an 80% efficiency. Now this is somewhat arbitrary, but this is a good conservative figure, 80% efficiency. Now if we 80% efficiency of 24, that means we have to subtract out 20%, and we get 19.2 inch ounces real energy gain up to this point. Now we have to add on the 12 inch ounces is the minimum amount of energy we need to lift the pendulum all the way to the 45-degree angle. That's the minimum amount needed. Now if our lifting process is 80% efficient, that means we have to add on a 20% efficiency loss of the system. That means we have to increase the weight, in a sense. We have to increase the weight we're lifting. We increase it by 2.4 ounces. So we add the 2.4 inch ounce efficiency loss to the minimum 12 inch ounces, and we get 14.4 inch ounces. This is the real energy needed to lift the pendulum all the way back to the 45-degree line. Now, 19.2 inch ounces is the real energy captured up to this point. We subtract out the 14.4 inch ounces, the real energy needed to raise the pendulum back to the 45-degree angle, and we get 4.8-inch ounces. Now this is a net energy gain, the final net energy gain. We could use this energy to do work outside the system. For example, to use this to turn an electrical generator to produce electricity. According to these calculations, my two-stage oscillator is a success. It is a free energy device. As far as I see it, there is no basic science rule against my two-stage oscillator becoming a free energy device. I think success or failure rests mainly with something called mechanical efficiency. A car engine is only about 35% efficient. This is the average car engine, while the average electric motor is 95% efficient. Other machines fall somewhere in between there. If I can make my two-stage oscillator, say, about 80% efficient, I'll succeed. If it's, say, down here at 65% efficient, then I will fail. For example, using this pendulum drawing as an example. Now, in my device, the pendulum goes the other way, but it doesn't matter what direction the pendulum goes in. In my device, stopped in half from the 45-degree triangle side. The distance in my device from the center to the edge of the triangle is about 9 inches. Stopping an inch and a half short means that the device is about 84% efficient. This side is the energy input. Right here is maximum kinetic energy. The pendulum then uses that energy to go upward. How efficient is it using the energy? It's about 84% efficient. Now, I see no reason in basic science that would prevent this pendulum from being more efficient. I could probably easily get to 90% or maybe even 95%. This mainly depends on the friction here at the axle of the pendulum. And on my device, it's a very crude axle. With a much smoother axle, I could probably get 90 or 95% efficiency. That in turn, if this was more efficient, that in turn would allow me to lift the load weight much higher. So in the end, the net energy gain, the true net energy gain, would even be greater. As I see it, basic science does not prohibit a two-stage oscillator from being a free energy machine. It's just a matter of how efficient you can make it.